For humans, the entire universe could not function without light. We see and understand things because of light. Without it, our eyes cannot see objects. In fact, we humans couldn't survive without the sun's light. Light plays a crucial role in understanding the structure and properties of everything, from atoms to the universe. This light raises many questions for humanity. Since ancient times, we have been trying to understand what light is. Light acts like a messenger of information. When it encounters an object, it reflects off that object, carrying information from it, then enters our eyes. Within a millionth of a second, our brain processes this information and helps us understand what we are seeing. Even though light is a messenger of information, it is itself invisible. That's why space appears so dark. We can only see the existence of light when it encounters an object. We see rays of sunlight because they pass through dust or gases. We already know that light travels at the incredible speed of around 300,000 kilometers per second and doesn't require any medium to travel. This is the maximum speed of our universe. It is a very special and unique property of light. Nothing else can travel at this speed. However, one of the greatest physicists of the 19th century, who worked on electricity and magnetism, predicted through his equations that light is just a part of radiation. Along with light, all radiation travels at the same speed. This radiation is called electromagnetic radiation or electromagnetic waves. Every charged particle in our universe has an electric field. An electric field is simply a distribution of force or lines of force. Electric field lines are the simplest way to understand an electric field. First introduced by the father of electricity, Michael Faraday. Electrons have a negative charge, so they have an electric field, while protons have a positive charge and also have an electric field. However, the fields differ depending on the charge. For a positive point charge, the electric field lines radiate outward, while for negatively charged, the electric field lines radiate inward. Simply put, the electric field originates at a positive charge and terminates at a negative charge. In the case of an isolated positive point charge, the electric field line starts at the charge and extends to infinity. For an isolated negative point charge, the electric field lines start at infinity and end at the negative charge. So this field exists around the charge at all times, even if there are no other charged particles nearby. Although the range of an electric field may be infinite, the strength decreases with distance, meaning the field is stronger near the charge. The electric field is responsible for electric force, where, like same charges repel each other and opposite charges attract. The field is always active. When two opposite charges come close together, the electric field of the positive charge links with the electric field of the negative charge. When two positive charges come close together, due to their similar outward fields, they repel each other. Magnetic forces were first observed in natural magnets. Similar to electric fields, magnets also have a field called a magnetic field. A magnet always has two poles, a north pole and a south pole. Magnetic field lines always start at the north pole and end at the south pole of the magnet. Like electric charges, similar magnetic poles repel each other, while opposite poles attract. The main difference between electric and magnetic fields is that in nature, negative and positive charges can occur independently of one another, whereas magnets always have two opposite poles. We have never found independent magnetic poles in nature with only north pole or only south pole. Even if a magnet is cut into two pieces, each piece becomes a new magnet with both a north and south pole. No matter how many times we cut it, the pieces always have opposite poles. Our universe operates with four fundamental forces: the strong force, the weak force, gravitational force, and electromagnetic force. Electromagnetic force is a combination of electric force and magnetic force. But why do we combine them? Why can't they be separate forces? The story of electromagnetism begins with the invention of the battery. In 1800, Alessandro Volta invented the battery, a device that pushes electrons from one place to another. This movement of electrons is known as electricity. An electron is a charged particle, so when a charged particle moves, it creates electricity. In 1820, Danish physicist Hans Christian Ørsted conducted a famous experiment. He placed a compass near a current-carrying wire. Naturally, a compass needle points in the direction of north and south pole direction of Earth. But when he placed near the current-carrying wire, the needle deflected from its original direction. This demonstrated that the movement of charges produces magnetic effects, which is why the compass needle was deflected. However, a stationary charge, no matter how large, has no effect on a magnetic needle. A charge must be moving in order to create a magnetic field. When charged particles move in a straight line, they produce magnetic fields around them. For charges moving in the opposite direction, the magnetic field will also be opposite. This can be easily explained by the right-hand rule. Point your right hand's thumb along the flow of current. Then curl your fingers as if wrapping around the wire. The direction your fingers point is the direction of the magnetic field created by the current. The 19th century was an incredible period for new inventions. At that time, the only source of electricity was the battery. But the demand for electricity was enormous. Scientists had to find a way to produce electricity other than by using batteries. Faraday worked on this problem. He asked himself if electricity could produce magnetism. Why couldn't magnetism produce electricity? After years of work, he succeeded in 1831. When a coil of wire is connected to a current meter and a magnet is moved inside the coil, the needle on the meter deflects. When a magnet moves forward, electrons start moving. When the magnet moves backward, electrons start moving in the opposite direction. A changing magnetic field causes electrons to move in different directions. If we place a light bulb, we can see that the bulb starts glowing because the moving electrons create electricity. This indicates that a changing magnetic field produces a changing electric field. With this discovery, we later created generators, which are used to produce electricity. Generators are simple. When we rotate a magnet, changes in its direction produce electricity. Thus, a charge will produce a magnetic field, but only if it's moving. A magnetic field will produce a current, but only if it's changing. A moving charge produces a magnetic field. But what happens if the moving charge suddenly changes direction? This phenomenon was explained very well by one of the greatest physicist mathematicians. Faraday's ideas on electricity and magnetism were put into mathematical form by physicist James Clerk Maxwell. He formulated 4 beautiful equations on electricity and magnetism. For easy understanding, let's review these formulas in simple terms. His first equation is about electricity. It states that electric charges, whether positive or negative, create an electric field. The second equation is about magnetism. All magnets have 2 poles. The magnetic field starts at one pole and ends at the other. Therefore, magnetic charges cancel each other out. This means there are no magnets that exist with only one pole. Magnets always have 2 poles, and their magnetic charges cancel each other out. The third equation explains that a charge in motion produces a magnetic field, and a changing magnetic field induces a changing electric field. These first 3 equations are relatively straightforward, and we already have some understanding of them. Now we move on to the next step. What happens when a charge accelerates? Acceleration means an object changes its speed or direction. A charged particle can vibrate, which means it continuously changes direction, and vibration implies acceleration. Let's observe the vibration in slow motion. First, the charge moves upward, creating a clockwise magnetic field around the charge. Then the charge moves downward, creating a counterclockwise magnetic field. This happens very quickly, so the magnetic field around the charge also changes rapidly. Now it becomes clear. We already know that changing magnetic fields can induce changing electric fields. So as the charge vibrates, the changing electric field induces a changing magnetic field, and the changing magnetic field induces a changing electric field. This process repeats continuously, propagating through space. The electric and magnetic fields work together to push each other along. This field conversion is called electromagnetic waves. At any point, the electric and magnetic fields are perpendicular to one another and to the direction of propagation. This is the fourth equation of Maxwell. Electromagnetic waves are produced whenever a charge is in accelerated motion. These waves don't require any medium to travel. They can propagate through a vacuum. If the charge stops vibrating, new electromagnetic waves won't be produced, but the waves already created will continue to spread. From his equation, Maxwell calculated that electromagnetic waves propagate through space at a constant speed of 300,000 kilometers per second and never slow down or stop. He realized the speed is very close to something familiar to us, the speed of light. This led him to conclude that light itself is an electromagnetic wave. However, the existence of electromagnetic waves was only a mathematical prediction by Maxwell. But in 1888, German physicist Heinrich Hertz produced electromagnetic waves in his laboratory and proved that their speed is 300,000 kilometers per second in a vacuum. This was the first experimental proof of electromagnetic waves. We know that accelerating charges produce electromagnetic waves. But why do charged particles accelerate? And how can light and electromagnetic waves be the same? To answer this, we need to understand the basic nature of waves. Like ocean waves, electromagnetic waves have crests and troughs. The crest is the highest point of the wave, and the trough is the lowest point. The center between the lowest and highest points is called the mean position. The distance from the mean position to the crest or trough is called the amplitude. This is the height of the wave, and amplitude is measured in meters. The distance between two consecutive crests or troughs is called the wavelength, which is also measured in meters. Its symbol is lambda. A crest and a trough together make up one wave cycle. If one wave cycle passes through a point in 1 second, the time period is 1 second or 1 hertz. If 10 wave cycles pass through a given point in 1 second, then it's 10 hertz, which is called the frequency. The number of wave cycles passing a particular point in 1 second is its frequency. Consider 3 electromagnetic waves traveling at the same speed. Since the speed of these 3 waves is the same, the number of wave cycles crossing a point per second would vary. For example, if the first wave cycle is long, fewer wave cycles will pass per second compared to the other 2 waves. So the first wave has a low frequency, while the third wave has a higher frequency. This means that a longer wavelength has a lower frequency and a shorter wavelength has a higher frequency. The frequency of a wave is inversely proportional to its wavelength. But how do electromagnetic waves have different wavelengths and frequencies? We know that electromagnetic waves are produced by the acceleration of charged particles, but not all charges accelerate or vibrate at the same rate. If a charge vibrates slightly, it produces lower frequency electromagnetic waves. If a charge accelerates rapidly, it produces higher frequency electromagnetic waves. So the intensity of vibration determines the frequency of an electromagnetic wave. The basic principle of electromagnetic waves is that their speed in a vacuum is equal to their wavelength multiplied by their frequency. If we multiply any given electromagnetic wave's wavelength and frequency, we get the speed of light. The speed of light never changes. For example, if we want to find the wavelength of an electromagnetic wave with a frequency of 900,000 Hz, We just need to use this formula. So, wavelength equals the speed of light divided by the frequency. In this case, we would find that the wavelength is 330 meters. The wavelength and frequency are directly related to each other. All electromagnetic waves carry energy, and the amount of energy depends on their frequency and amplitude. The higher the frequency, the more energy. The lower the frequency, the less energy. Electromagnetic waves come in different wavelengths, frequencies, and energies, so we classify them into different categories. We already know that the distance between two consecutive crests is called the wavelength. The longest electromagnetic waves are 100,000 kilometers long, with a frequency as low as 3 Hz. Electromagnetic waves can theoretically have wavelengths as long as 1 billion kilometers, but such wavelengths are undetectable because their frequency is less than 1 Hz. Even at a speed of 300,000 kilometers per second, such a wave wouldn't complete 1 cycle per second. So the energy becomes undetectable. The shortest electromagnetic waves have a wavelength of 10 to the power of -12 meters or even smaller, with a frequency of 10 to the power of 24 Hz or more. Based on wavelength and frequency, we categorize electromagnetic waves into different groups: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. The most extreme waves are gamma rays, which have extremely high frequency and energy. Depending on their frequency, their energy varies. The human eye can detect only a certain range of electromagnetic waves, between wavelengths of 380 nanometers and 760 nanometers, which we call visible light. Since visible light is familiar to us, we will start with this group. Unlike other groups, it's very special because we see things and understand the universe through visible light. To understand visible light, we need to look into Bohr's model of the atom. Electrons orbit the nucleus in different energy levels, and these energy levels vary by atom. Energy is measured in electron volts. For a hydrogen atom, the first shell's electron has -13.6 electron volts. The second shell has -3.4, the third shell -1.5, and so on. The energy of electrons in atoms is quantized, meaning that the energy of the first shell is fixed at -13.6 electron volts. It cannot be -13.7 or -13.5. This is the same for all hydrogen atoms in the universe. In nature, electrons orbit in their ground state, but when they gain energy, they jump to a higher energy level. For example, imagine an electron in a hydrogen atom gains some energy, and it jumps from the second orbit to the third orbit. The electron in the second orbit has -3.4 electron volts, and in the third orbit it has -1.5 electron volts. This means the electron gained 1.9 electron volts of energy. That's why it jumped from the second to the third orbit. As we have seen before, electrons always prefer to be in the lowest available orbit, so they eventually return to a lower orbit. Return means it undergoes acceleration, and its velocity changes. When a charge is accelerated, it emits electromagnetic radiation. We know that the wavelength, frequency, and energy of electromagnetic waves depend on the rate of acceleration or vibration of the charge. When an electron moves from the third orbit back to the second orbit, it emits an electromagnetic wave with an energy of 1.9 electron volts. This energy packet is called a photon. Electromagnetic waves and photons are the same. Particle nature of electromagnetic waves are photons. There is a formula for converting energy into wavelength, and in this case, we find that the electromagnetic wave has a wavelength of 654 nanometers. The visible light range starts from a wavelength of 760 nanometers to 380 nanometers, which we call the visible light spectrum. A wavelength of 654 nanometers corresponds to red light. In the visible light spectrum, red light has the longest wavelength, while violet has the shortest wavelength. The energy range for visible light from red to violet is 1.63 electron volts to 3.26 electron volts. Any energy released within this range is visible light. If an electron in a hydrogen atom jumps from the fourth orbit to the second orbit, it emits electromagnetic waves with an energy of 2.55 electron volts, corresponding to a wavelength of 488 nanometers, which is green. Thus, we have red light, green light, blue light, violet light, and many others. They differ only in wavelength, frequency, or energy. The perception of color that something happens in our minds. White light consists of all color wavelengths, but when it strikes an object, most of the color wavelengths are absorbed by the object's atoms, leaving only red light to be emitted. That's why red objects appear red. A wavelength of 654 nanometers is emitted by just one hydrogen atom at a time. But the Sun contains 10 to the power of 57 hydrogen atoms. Due to the extreme pressure of the Sun's inner core, atoms heat up and gain varying amounts of energy, causing electrons to jump between different energy levels. Depending on the distance of their jumps, they emit electromagnetic waves of different wavelengths. Electromagnetic waves are not only emitted by the Sun's inner atoms. In the Sun's plasma, countless free electrons vibrate randomly, also emitting electromagnetic waves of various wavelengths. Plasma refers to the part of the Sun where unpaired electrons and nuclei exist. Moreover, there are trillions of stars in the universe, all emitting electromagnetic radiation. All high-temperature objects emit visible light, electromagnetic waves. Humans also emit electromagnetic radiation, but not in the visible light range. Infrared radiation lies just beyond red visible light, with wavelengths between 760 nanometers and 1 million nanometers, or 1 millimeter. When an object is not quite hot enough to radiate visible light, it emits most of its energy in the infrared range. Infrared radiation has an energy range of 0.0012 electron volts to 1.65 electron volts. For example, if a molecule releases 1 electron volt of energy, its wavelength is 1,240 nanometers, which falls in the infrared range. Infrared radiation is produced by the vibration and collisions of molecules within an object. You might wonder how neutral molecules, which have no charge, can produce electromagnetic waves. Take the carbon dioxide molecule as an example. It consists of one carbon atom and two oxygen atoms. Carbon has 6 electrons and oxygen has 8 electrons. So the molecule has 22 protons and 22 electrons, making it electrically neutral. However, the electron distribution is uneven. The atom with more electrons pulls the atom with fewer electrons. So in this case, the oxygen atom pulls the carbon atom more strongly, creating an electrical imbalance between atoms. The atom with more electrons becomes a negative pole, while the atom with fewer electrons becomes a positive pole. Even though the overall molecule is neutral, it has 2 electrical poles and is called a dipole molecule. When the charge oscillates, it produces electromagnetic waves. During molecular vibration, these charged poles stretch or vibrate, producing electromagnetic waves. The frequency of electromagnetic waves depends on the frequency of molecular vibration or rotation. Each molecule has a different range of vibration modes. For instance, when carbon dioxide absorbs the right amount of energy for vibration, it produces a wavelength of around 1,000 nanometers. Thus, carbon dioxide can absorb or emit electromagnetic waves with a wavelength of around 1,000 nanometers. Heat causes molecules to vibrate. Since heat is the primary source of infrared radiation, any object with a temperature emits infrared radiation. Even objects we think of as cold, such as ice, emit infrared radiation. In fact, an object with a temperature above absolute zero emits radiation. Absolute zero temperature is minus 273 degrees Celsius, and achieving absolute zero is physically impossible. Our average body temperature is 37 degrees Celsius, so we constantly emit electromagnetic waves with wavelengths of around 10,000 nanometers, which are infrared. As we can see, the wavelength of electromagnetic waves depends on how hot objects are. As heat decreases, the intensity of electromagnetic radiation decreases, causing the wavelength to increase. Hotter objects release shorter wavelengths because their atoms vibrate more rapidly, while cooler objects release longer wavelengths. Since infrared lies beyond the visible light spectrum, we cannot see it. But some animals such as snakes and frogs can detect it. Even though we cannot see infrared radiation, we can feel it as heat. However, we have managed to create infrared cameras that help us see infrared radiation, which is useful in many industries. At night, when there is no visible light, all objects on Earth become dark, but they still emit infrared radiation. With the help of infrared cameras, we can see objects in the dark. Microwaves have wavelengths longer than infrared waves, ranging between 1 millimeter and 1 meter, with corresponding energy ranges from 0.0012 to 0.000012 electron volts. We are most familiar with microwaves because they cook food rapidly. Every food contains water molecules, and these water molecules can absorb specific ranges of electromagnetic waves. In a microwave oven, there is a vacuum chamber with magnets and electrodes called a magnetron, which produces a specific range of electromagnetic waves. When these waves encounter water molecules, they cause the molecules to vibrate and rotate. These vibrations and the resulting friction between the molecules generate heat, cooking the food quickly. In household microwave ovens, we typically use electromagnetic waves with wavelengths of 122 millimeters. Microwaves are reflected by metals but can easily pass through plastic or glass, which is why we use plastic or glass containers to cook food in the microwave. Microwaves are also used for long-distance satellite communications, radar systems for spacecraft navigation, and measuring the speed of vehicles. In the electromagnetic spectrum, radio waves have the longest wavelengths and the lowest frequencies. Their wavelengths range from 1 meter to 100,000 kilometers, with frequencies ranging from 300 megahertz to 3 hertz. 1 megahertz is equal to 1 million hertz. At 300 megahertz, the wavelength is 1 meter. Due to their long wavelengths, radio waves are considered the safest form of non-ionizing radiation. Since their wavelengths are long and their frequencies low, they have low energy. The energy of radio waves ranges from 0.0000012 electron volts to 10 to the power of minus 14 electron volts. Non-ionizing radiation doesn't have enough energy to remove tightly bound electrons from atoms, so it doesn't cause damage to the cellular structure of our bodies. However, long-term exposure to radio waves with higher frequencies can increase body temperature. Radio waves are produced by charged particles when they accelerate. We artificially produce radio waves more than any other type of electromagnetic wave by moving electrons back and forth in a device called an antenna. Naturally, these waves are produced by lightning and astronomical objects such as galaxies and nebulas. We have seen that electromagnetic waves with longer wavelengths than visible light have lower frequencies and energies, making them non-ionizing radiation. Thus, they are safe for use in everyday life. Wavelengths from 700 nanometers to 100,000 kilometers are considered non-ionized radiation. Non-ionized radiation cannot break the atoms and molecules in living organisms. However, electromagnetic waves with wavelengths shorter than visible light are extremely high in frequency and energy, making them very harmful. Ultraviolet radiation makes up about 10% of the total electromagnetic radiation from the sun. UV wavelengths range from 400 nanometers to 10 nanometers, with energy levels between 3.1 and 12 electron volts. Like visible light, ultraviolet radiation is emitted by excited electrons. For example, consider the Bohr model of a hydrogen atom. The electron in the first orbit has minus 13.6 electron volts, and in the second orbit it has minus 3.4 electron volts. If the electron gains enough energy, it can jump from the first to the second orbit. When it returns to the first orbit, it emits 10.2 electron volts of energy, which corresponds to a wavelength of 122 nanometers. Since ultraviolet waves fall between 400 and 10 nanometers in wavelength and between 3.1 and 12 electron volts in energy, an electron returning from the second to the first orbit in a hydrogen atom releases ultraviolet radiation. Similar to hydrogen atoms, mercury, helium, and carbon atoms are also major sources of UV radiation. Ultraviolet radiation is divided into three groups based on wavelength, frequency, and energy. UVA, that's 400 to 320 nanometers, UVB, that's 320 to 280 nanometers, and UVC, that's 280 to 100 nanometers. UVC is the most harmful form of UV radiation. But how exactly is it harmful to humans? Our bodies function based on DNA, which instructs cells on how to work. DNA consists of complex molecules. Molecules are made of atoms, and when UV radiation enters DNA molecules, it causes electrons within the atoms to absorb energy and jump to higher energy states. This sudden change in electron position can break the bonds between atoms in the molecule, causing the structure of the molecule to collapse. This molecular collapse leads to damaged DNA. Since damaged DNA can no longer properly instruct cells, the result is malfunctioning cells. This can lead to harmful conditions such as cancer, skin burns, eye damage, and a weakened immune system. Fortunately, most UV radiation is absorbed by the ozone layer. The ozone layer contains ozone molecules, and when UV radiation strikes these molecules, it breaks them apart into dioxygen, that's O2, and individual oxygen atoms. This process absorbs the energy of the UV rays, preventing them from reaching Earth's surface. The individual oxygen atoms then recombine the dioxygen to form ozone molecules again. This continuous reforming cycle of ozone protects life on Earth from harmful ultraviolet radiation. X-rays have wavelengths shorter than ultraviolet waves, ranging from 10 nanometers to 0.01 nanometers, with equivalent energy levels between 12 electron volts and 120,000 electron volts. When high-energy photons strike an atom, they can eject tightly bound electrons from the atom's inner shell, ionizing the atom by causing it to lose an electron. As we know, electrons always seek to fill the inner shell. So when higher energy shell electrons fall into the inner shell, they release X-rays. X-rays can also be produced when high-energy, negatively charged free electrons pass near the positively charged nucleus of an atom. As the electrons are deflected by the nucleus, due to the attraction between opposite charges, this sudden change in direction emits a continuous X-ray spectrum. This process is called Bremsstrahlung radiation. We produce X-rays by sudden collision of high-speed electrons. Although X-rays are more harmful than ultraviolet rays, we have developed ways to manage and use them safely. Gamma rays are extremely high-energy electromagnetic waves, and their wavelengths are billions of times smaller than those of visible light. Their wavelengths range from 0.01 nanometers to 10 to the power of -7 nanometers, and their energy levels range from 120,000 electron volts to 10 million electron volts. These are extremely high-energy photons. Gamma rays are produced during extreme cosmic events, such as when a star dies and becomes a neutron star or black hole through a supernova explosion. These supernova explosions emit highly energetic electromagnetic waves. Neutron stars have very strong magnetic fields, and when charged particles become trapped in these fields, they accelerate to nearly the speed of light. As a result, they emit high-energy photons, gamma rays. Our sun also emits gamma rays. In the sun's inner core, the process of nuclear fusion constantly takes place. When hydrogen atoms fuse to form helium, gamma rays are emitted. These gamma rays travel from the inner core to the sun's atmosphere, where they collide with atoms, gradually losing energy. By the time they reach Earth, they have lost most of their energy and become non-ionizing radiation. Similarly, gamma rays are produced during nuclear fission. When heavier nuclei split into two smaller nuclei, gamma radiation is emitted. We have harnessed this process from nature to develop nuclear weapons. If cosmic gamma rays were to directly enter our bodies, they would tear apart atoms and cause severe damage. High-energy electromagnetic waves are incredibly harmful to living organisms. Fortunately, Earth's atmosphere acts as a protective shield, blocking most of these cosmic threats. However, while the atmosphere protects us from external cosmic dangers, humans have developed nuclear weapons, which could explode at any time due to poor decisions by world leaders. Thus, the greatest threat to humanity may not come from the outside, but from humanity itself.